Well, hello everybody. Dave here today to start our series of lessons on thermodynamics. We're going to start off by talking about gases and their properties associated with the ideal gas law and how we relate that to the average kinetic energy of the molecules. We'll then move on to heat transfer and the idea of the laws of thermodynamics themselves, and we'll finish up our series with a discussion about heat engines, refrigerators, and the Carnot cycle. To begin our discussion of gas, we want to talk about the factors that affect a gas with thermodynamic processes. The four variables that you see before you here are the essential variables when discussing gases. The first, and one that you would recognize if you've done any studying in chemistry, is the idea of small n, which in this case is going to be the quantity of gas in a unit of moles. That is a number directly related to Avogadro's number. The temperature of the gas is going to be in Kelvin and not another unit, which means typically we're going to have temperatures in degrees Celsius, which we'll have to convert. I've given you the conversion rate right there, related to absolute zero. The pressure of a gas is going to be similar in discussion to the pressure that we discussed with fluids, where we dealt with the force per unit area. In this case, we're going to talk about the physical pressure that the gas exerts on something like a cylinder or the side walls of a container. We're going to deal with those units in terms of pascals, which is the SI unit for pressure. The volume of the gas is our last unit that is essential in understanding, and we're going to deal with this in terms of cubic meters. So you'll notice again that units are going to play an essential role, and the units have to be the ones that are listed. Together, these variables are all related to each other by what is called an equation of state for the gas. This idea of an equation of state probably sounds quite complicated, and that's because it actually is. What we do to simplify the problem is we maintain the gas at a low pressure, and what results is all gases behave generally the same in this idea called an ideal gas. And so the definition we will use for an ideal gas is a collection of atoms or molecules that move randomly and exert no long-range forces on each other. In physics, if these long-range forces were existing, we would actually have to consider those in the overall motion of the molecules themselves. So this randomness is going to be essential when we get into that discussion. The other property that's going to be vital is the idea that they're point-like and they don't have a consequential volume, that they are going to negate the volume of the atoms themselves. So in our early understanding of these variables, the best we could do is make experiments by which we held some of these variables constant and played around with the others to see if we could see a relationship between the two. And so what we did is we take something like this cylinder and we put a piston on it that can move to change the volume. We assume that there's no leak, which means that the number of moles of gas in this cylinder will remain constant. Well, there's four variables. We've just stated that one's going to be constant throughout all these experiments. Now out of the remaining three, we're going to choose one to stay constant and see how the two relate to each other. So for our first experiment, we're going to keep the temperature constant. And what was observed is that the pressure of the gas was inversely related to the volume. You can see from the mathematics what we've done is we've taken the proportionality and we've actually put in a constant of proportionality, in this case a lowercase k. If we move v up to p so that we have pv is equal to this constant of proportionality, what we end up with are two situations. We have the initial state in which we have a pressure and a volume, which we've labeled as P naught and V naught. Well, that's equal to the proportionality constant. At some time later, we have a different pressure and a different volume. Well, based upon this equation, that's also going to be equal to the proportionality constant. The fact that those two quantities are equal to the same constant mean they're also equal to each other, and what we end up with is P naught V naught is equal to PV, which is so lovingly known as Boyle's law. So again, this is only in the state of constant temperature with the already made assumption that the number of moles won't change. In the second experiment now, let's go ahead and let temperature change, but let's keep the pressure constant. What was observed then was that the volume of gas is directly related to the temperature. We see again from the mathematics what we've done is we've taken the proportionality and we've input a constant of proportionality k. We've solved for k in that v naught over t naught and v over t are two different states of this gas. Again, because they are equal to the same constant, they are equal to each other, which means this statement of v naught over t naught is equal to v over t is a new law based upon this constant pressure known as Charles' law. So for the third experiment, what we did is we kept constant volume and we allowed pressure and temperature to change. And when this experiment was done, it was observed that the pressure of the gas is directly related to the temperature. So for a third time, we take this proportionality and we change it into an equation where we have a constant of proportionality K. We solve the initial state for K to end up with P naught over T naught. We change the situation so that there is a new state of pressure and temperature. We again solve for the constant proportionality and we end up with P over T. Because these are both equal to the same constant of proportionality, we end up with a statement of P naught over T naught is equal to P over T. We've given credit for this law to Gay-Lussac. So now we had these three separate laws that were all talking about the same variables but keeping different variables constant. And it seemed inefficient in that we didn't have one equation of state to be able to describe all of these scenarios. Well, Clapeyron came around and he was able to actually take these three laws and combine them into one equation of state that we now know to be the ideal gas law of PV equals nRT. Now this value of R is known as the universal gas constant because experimentally what we found is with several gases, if we took the ratio of PV to NT, what happened every time we took the pressure to 0 was that the ratio always approached the same value, which in our case is 8.31 joules per mole Kelvin. So it's important to recognize that this value is going to be used no matter what type of gas it is. But at the same time, it's also really important to recognize that you can see in the units that hardwired in is the temperature in units of Kelvin. So now that we have this equation of state that deals with the macroscopic properties of the gas, we can begin to redefine this equation of state in terms of the microscopic particles themselves. And for that, we have to go back to our definition of moles. And we'll remember that moles are equal to the total number of particles in a substance divided by Avogadro's number. It may be interesting to note that the official definition of a mole is the amount of a substance that contains as many particles as the number of atoms in 12 grams of carbon-12 isotope. Well, that's interesting because now if we define something known as the atomic mass unit, we know that the atomic mass in atomic mass units of a substance is numerically the same as the molar mass of the same substance. So you can actually read the periodic table to get what the molar mass is directly. If we take this value and substitute it in to our equation of state, what we see is that we've actually redefined PV in terms of the number of particles and this new constant known as Boltzmann's constant. And by definition, it is the ratio of R to Avogadro's number. So we've begun our discussion now of the microscopic understanding of the gases themselves. And for that, we have to turn to the kinetic molecular theory of gases. And there are 5 statements that are true in this discussion of the kinetic theory. The first is that the number of molecules in the gas are large, and the average separation between them is large compared with their dimensions. The molecules obey Newton's laws of motion, but as a whole, they move randomly. This randomization is important because we're actually touching a subtopic of physics known as statistical mechanics. And the statistical end of this requires that randomization take place. That is well beyond the scope of this lesson, but it's certainly an interesting and complex topic to cover. The third is that the molecules interact only through short-range forces during elastic collisions. So the idea of a molecule bouncing off the sidewall of a container is absolutely fine. But remember that when we defined what an ideal gas was, we said that there was no long-range forces present. This is where that is absolutely essential. The fourth is that the molecules make elastic collisions with the walls. So you know that there are 2 types of collisions, and we are going to say at the atomic level that all we see are elastic collisions, meaning that there is no energy loss to things like heat. And finally, the 5th one is that all molecules in a gas are identical. It would be really difficult to generalize our statements if we had all the molecules in a given gas having slightly different properties. With an understanding of this theory, let's imagine now a container that is cubic with an edge length of d. What we'll do is we'll track the motion of one molecule as it's moving with a velocity v in whatever direction it wants. Remember, we're considering this to be random. What we'll do is we'll focus on the 3 directions of x, y, and z and see if we can't make some generalized statement about the pressure on the sidewall as well as the velocity at which it's traveling. And so if we're dealing with the x direction first, again, we're assuming that it's going to collide elastically with the sidewall, which means that it's going to have an impulse imparted on it to be 2 mvx. Remember that our impulse, by definition, is the final momentum in the x minus the initial momentum, but since there's no change in velocity going in or coming out, inevitably what we have is 2 times the momentum of the particle. So knowing this change in momentum, we can actually find the force that this molecule applies on the sidewall if we redefine Newton's second law in terms of momentum. Hopefully you learned at some point that F equals ma can be rewritten if we consider acceleration to be delta v over delta t. If that's the case, what we actually end up with is delta p over delta t as a definition of the net force. This is the more usual definition that's used at the college level. Given the equation that we have for delta p, we can plug that in, but we can see that we don't have an expression for delta t yet. However, what we do know is that these molecules are moving randomly, and from one collision to the next, what's going to happen is this particle is going to move an entire distance d to the other side of the box, and then an entire distance d back to the original side that it hit, which means that given this constant nature of the velocity in the x direction, we can have a time interval to be delta t is equal to 2d over vx. So again, this is the assumption that the velocity in the x direction and y direction and z direction are going to be constant throughout this motion. Well, when we substitute that into our equation for force, what we end up with is this equation relating force to mvx squared and the side length d. Well, that's the force of one of the particles. What if we want to find the force of all of the particles? Then what we would have to do is we'd have to take the sum of all of the forces of all of the molecules hitting the side wall, which is what the second equation is trying to represent. What we do know is that the average of the square velocity in the x direction is related to the number of molecules. And so if we have n number of molecules, that means we have n number of velocities that we're going to add up squared. And so we can actually find the average x direction velocity of the molecules to be the sum of the squared velocities divided by the number of molecules. What's even more interesting is the fact that if the collisions are indeed random, then the average velocities in the y direction and z direction are equal to the velocity in the x direction. This is the nature of the randomness. This is the statistical end that's exceptionally difficult to understand without a further discussion into this idea of statistical mechanics. But given this statement, if we use the Pythagorean theorem to relate these components to the total velocity, knowing that they're all equivalent to each other, we can actually end up with an equation that states that the average velocity in the x direction squared is equal to 1/3 of the average velocity total squared. So now that we have this new equation for vx squared, we can actually substitute it into our equation for total force to get the equation that you see before you. Now it's starting to look like kinetic energy, but remember that kinetic energy is 1/2 mv squared. So there's still something funny going on. But if we take a look at the discussion of pressure associated with the sidewall, how much pressure the gas is actually imparting on this sidewall is the same as any sort of pressure that we've discussed in the past. It's the force per unit area. Well, we have our equation for force at the top, and the cross-sectional area that it's hitting is just d squared because this is a cubic container. And so when we substitute these two ideas together, we end up with the equation of 1/3 times n over v mv squared. Well, this sure looks really close to kinetic energy, except for we're missing that 1/2. So now we have this equation for pressure in terms of these quantities, but we want to make it specifically about the average kinetic energy of the molecules. We know that we have an mv squared component, but what we need is that 1/2. So what we do is a bit of a mathematical trick. We multiply the top and bottom on the right-hand side by 2. And what we can do then is rearrange this equation so that we end up with 2/3 n over v times 1/2 m V average squared. And what this is now is this is an equation for pressure in terms of the number of molecules, the volume by which the molecules are contained, and the average translational kinetic energy of these molecules. So all of a sudden we've taken this macroscopic quantity and we've defined it in terms of these microscopic particles. So we're going to do one more thing with this equation for pressure, and we're going to multiply both sides by V, so that now we have the quantity of PV is equal to the quantity on the right hand side. But what we're going to do now is we're going to bring in the redefined ideal gas law in terms of the number of particles, the Boltzmann constant, and temperature, and we're going to solve that new equation for T to get the equation that you see before you. So temperature is equal to 2 divided by 3 times the Boltzmann constant times the average translational kinetic energy of the particles. Well, folks, this is hopefully what your teacher has defined temperature to be, is the average kinetic energy of the molecules. This here now is the mathematical proof of that statement. If we want to find the total translational kinetic energy in terms of temperature now, what we can understand is, well, if we have the average kinetic energy of a molecule, all we need to do is multiply it by the total number of molecules, in this case capital N. Well, that gives us the two equations of either 3/2 nkt or 3/2 nRT. And folks, these are great equations because what they are now going to tell you is, given the properties of the gas, we can actually determine the total kinetic energy that exists in that gas. To simplify this a little bit, if we consider a monoatomic gas, then the translational kinetic energy is the only type of energy that the molecules can have. And so what we've also done now is we've derived an equation for the internal energy of a monoatomic gas as 3/2 nRT. This idea of internal energy is going to be essential when we start to discuss the laws of thermodynamics. One final quantity that's worth mentioning is this idea of the root mean squared speed of the molecules. And simply what this is we have the average speed squared of the particles. Well, if we take the square root of that, what we end up with is this quantity called the root mean squared, or the RMS speed. Well, if we use our equations that we've already derived, then we know that this is either going to be the square root of 3 kBt over m, or the square root of 3RT over capital M, where m is the molar mass in kilograms per mole. So what we've done now, folks, is we've given ourselves the ability to find the average speed that the particles will have given these particular variables of the gas. So there you have it. We have two different discussions of gases in terms of the macroscopic properties and the microscopic properties. With the macroscopic, we went through the observations that were made holding certain variables constant, which inevitably led us to the ideal gas law. We redefined the ideal gas law in terms of particles and the motion of particles, and from that we were able to discuss things like pressure and temperature in terms of the average translational kinetic energy themselves. Next up, thermodynamics and their laws. Have a great day, everybody. We'll see you again.